Hi, everyone, and welcome to the MIT Robotics Seminar. It's a great pleasure for me to introduce today's speaker, Professor Tim Barfoot. Tim is a professor at the University of Toronto, where he's also the Associate Director of the Robotics Institute, and he's also a faculty affiliate of the Vector Institute. Tim got his PhD from the University of Toronto, and before becoming a faculty, he worked at NDA Robotics, which is the company that made the Canadarm manipulator that many of you might know about. It's essentially the robotic arm which went on the Space Shuttle and the International Space Station. He was also a visiting professor at the University of Oxford back in 2013 and was director of autonomous systems at Apple in 2017 and 2019. Tim is working in the broad area of autonomous mobile robots and is interested in developing methods spanning localization, mapping, planning, and control to allow robots to operate over long periods of time in large-scale, unstructured, and 3D environments. And for his work, he has been recognized with a number of awards, including 2 best papers at ICRA, an early research award from the province of Ontario, and a Canada Research Chair. Moreover, he's an IEEE Fellow and a faculty advisor of the University of Toronto self-driving car team that won the SAE Autodrive competition for 5 years in a row. Impressive. Okay. So Tim is a member of the editorial board of IJRR, the Transaction of Field Robotics, and the foundation board of Robotic Science and Systems. And he served as the general chair of the Field and Service Robotics Conference in 2015. Finally, he's the author of the book State Estimation for Robotics, which is a must-read for people working in state estimation and SLAM. And without further ado, let's welcome Tim.
Just an audio check. You guys, is the mic working okay? Yep, great. Well, thank you so much for the invitation and the lovely introduction, Luca. I've had some really wonderful discussions throughout the day already today, so let's keep the dialogue going. I wanted to give a talk today that's a little bit of a mixed bag of different things, but it falls under I guess, a single theme, which is, to get many of these applications of particularly mobile robots out there in the next little while, there's sort of a long tail of issues that we're having to deal with to kind of enable these applications. So my title, Taking a Hard Line, Robot Navigation when Lighting, Weather, and Geometry Won't Cooperate. And we were talking about this earlier today, but a little bit of just philosophy of the group. Our group does curiosity-driven bottoms-up research where we're just kind of exploring new algorithms and what we can do with them. And then we also get very involved, mainly because of the way the Canadian funding structure is with industry, where we actually try out a lot of these algorithms on sometimes very large robots out in the world. And I think really it's this sort of iterative process of trying things out and then going back to the drawing board and kind of going in that circle that makes for a good robotics research group. So this is my graphical outline of the talk today. I'm going to try to squeeze in 4 different topics under this overall theme of sort of driving down the edge and corner cases of some of these navigation problems. You don't need to read all the little details, but those are all I can share the slides after, but those are all sort of the papers that came out in the last 2 years. So we'll briefly talk a little bit about some new sensors that we're working with that exploit the Doppler effect to get new velocity information. I'll talk a little progress update on our ability to do localization on the road, particularly with radar. I'll give an update on some of the stuff we've been doing on off-road driving and an extension of a technique that we've worked on for a long time called visual teach and repeat. And then I'll sort of switch gears and talk about some stuff more in the back end of robot navigation, which are these certifiably optimal algorithms, which much of that work started here. So hopefully there's some friendly ears to listen to that stuff. So let's dive in with the first topic, which is Doppler odometry. So one of the things I've really enjoyed over my career is getting my hands on sensors that people maybe don't typically make use of in robotics. So this is just a little bit of a history slide of some of the things that we played with maybe before they become popular and maybe still haven't become popular. Everything from sun sensors that came from microsatellite technology for getting very low-cost orientation in the field, to star trackers for the similar purpose over here on the bottom right. This is like the size of a deck of cards, and it can produce pretty much an orientation or a rotation matrix directly from a single observation of the sky at night, obviously. And we even got our hands on some Lidar sensors that were able to produce sort of image quality intensity data long before the current products that we can think of today. And we were doing things like trying to treat this as an image and doing computer vision on this in order to do sort of real-time motion estimation by even extracting things like surf features long before we had deep learning to do estimation of motion. And so, following with this theme, the sensors that we're playing with today that I think are kind of maybe a little bit ahead of the curve and are very interesting are radar. Radar is kind of an old sensor. It's been around since World War II. I saw a really cool radar antenna over in the CSAIL building just a few minutes ago. But radar and robotics is still kind of an undersubscribed technology, I would say. And so we're trying to think about what we can do with that. And then how many people have heard of a Doppler Lidar? So this is quite a fun, relatively new technology. There's a couple of companies that make these optical sensors that can now use the Doppler effect to get per point velocity, radial velocity on every point in a point cloud. And so we've been thinking about what we can do with that. This company, EVA, was started by some of my colleagues from Apple in the sensor hardware team that left and did a startup. And they asked if I could play around with the sensor and see what I could do with it. So we'll talk a little bit about trying to do odometry from this Doppler Lidar. And for those that maybe need just a little reminder of what the Doppler effect can allow us to do. So these sensors that use the Doppler effect are basically using a slightly different ranging principle than the typical Lidar or radar. Well, radar always does it this way, but Lidar doesn't always do it this way. So they use frequency modulated continuous wave to do ranging. And the idea is you're sort of sending out a signal that has an increasing frequency. And in the frequency space, that looks like a kind of a chirp. That chirp bounces off something, and when it comes back, it's time shifted. And by actually measuring the frequency shift in that return chirp, you can get some measure of the range to the object. And because there's another effect that happens, which is the Doppler effect, which also causes a small frequency shift if the relative motion between the sender and the receiver is non-zero, you kind of get these two confounding frequency shifts. And so the radars that we use and the lidars that we use, what they do is they first send an up chirp and then they send a down chirp. And then those frequency shifts basically, one of them stays the same sign, the other one shifts sign, and you get two equations and two unknowns, and you can solve for both the range and the velocity to the target, which is pretty cool. So that's kind of just a quick synopsis of how Doppler ranging works. And then as we start to talk about what we can do with these Doppler lidars first, there's a few advantages that I kind of see. There's sort of an obvious thing that happens, which is you can actually get segmentation of moving objects almost trivially from the data by just sort of thresholding on the relative velocities between you and the scene. We're not actually going to do that in what I'm going to talk about, but that's a nice application of this type of sensor. What we will see in the next few slides is that we can handle sort of geometrically degenerate situations. So if you're driving, I came through a fairly long tunnel on the way from the airport last night to my hotel. And if you were trying to do something like iterative closest point, where you're matching point clouds to estimate your motion along that tunnel, you would get into some tricky scenarios there where there's an infinite number of solutions along the length of the tunnel to do that matching. However, with the new velocity information, we can now actually solve for our motion much better in these geometrically degenerate situations. And then another kind of fun thing on the far right is you're looking right now at a video. This is actually now a video from the Doppler Lidar in the middle of a snowstorm. And because you're sending two chirps, if you don't get a valid solution from that two systems of equations and two unknowns, you actually don't get valid data. Here's data from a Velodyne, which is just using one pulse to get return. And you can see in the Velodyne data, there's just a lot of clutter from the snowflakes that are falling from the sky, whereas you almost get for free rejection of precipitation from the data in the Doppler Lidar. So that was just kind of a fun thing that we noticed. I'm not even sure that the sensor manufacturer knew that was going to be something that would work out, but that was kind of fun. So again, you don't have to solve all of these long tail problems in software. Sometimes you can solve some of them by improving the hardware, right? And so as roboticists, I think we need to think about both parts of the puzzle. We're really systems engineers that are trying to put the whole system together. So I've got a Doppler Lidar. I now have this new radial velocity information. What can I do with that? And so the first thing that we set our minds to was trying to estimate motion, so trying to do odometry. And you could imagine building some kind of a motion estimator that is using a number of different sources of information. So we might be accumulating some point clouds into a map. We're then moving, and as we get observations from the LiDAR range information, we sort of build these factors that go back to the map. So those are sort of typical range factors. We might also have some motion estimation factors that try to encourage smoothness in our trajectory. And then the new bit is that we can incorporate these per timestamp velocity information factors at every time that we acquire data. And so we can actually put that all together. That's sort of the obvious thing to do, put that all together into a big factor graph problem and solve that for the motion of the frame, of the LiDAR from one frame to the next. And we actually do this in like a sliding window form. So very, very typical sort of nonlinear least squares optimization problem with this new velocity information coming in. This is a bit of an eye chart, but we've done a lot of testing on this on a real car where we gathered data. And the net of it is that in situations like tunnels, our algorithm is sort of the fourth row in each one of these things. We're doing a lot better than the typical algorithms, particularly in the geometrically degenerate situations like tunnels. But somewhat surprisingly, also in less degenerate situations like highways, where there's not a lot of stuff off to the side of the highway, or there's just a lot of other moving vehicles, we can actually do pretty well. And just to sort of show you, like qualitatively, this is the data from the Doppler Lidar on the top. Here's sort of our motion estimate compared to ground truth over the scale of 7 or 8 kilometers, and we're sticking pretty close to the right answer. And the places where you really notice the differences are, as I said, in things like tunnels. This was an example of the Robin Williams tunnel, and it's about 300 meters long. And you can kind of see a typical iterative closest point algorithm is this orange line. It actually estimates the motion much shorter than the true length of the tunnel, whereas by using the velocity information, we're able to keep track of our motion much better and not sort of biased towards no motion, which is what most algorithms tend to do without velocity. So yep, our errors drop down quite a bit in those scenarios. So a little bit of an obvious thing to do, but a nice way of solving a problem that's pretty hard by just changing the hardware. The next thing that we thought about with this Doppler Lidar odometry was, could we actually do away with using the point cloud part altogether? Well, we're using the point cloud, but we're really focusing more on the velocity information. A typical iterative closest point algorithm is going to require computing correspondences at each iteration between every point in the first point cloud and points in the second point cloud. And that's the most expensive step. So what we thought about next was, could we actually just directly estimate the 6-degree freedom velocity from these radial velocity measurements and then just integrate that after the fact over time to get motion? And it turns out you can under some caveats. With only one Doppler LiDAR, because you're only getting radial velocity information, there's actually an observability issue. You can only measure the translational velocities in 3 degrees of freedom from a single LiDAR. You can't get any of the 3 rotational angular velocities. However, we actually did a little bit of an exploration, and it turns out that you could put more of these LiDARs that were not co-located on the roof of a car, and it turns out, at least in theory, if you have 3 of these LiDARs, you can actually recover the full 6-degree of freedom velocity of the entire platform. And it's sort of the non-co-location that's quite important that allows you to recover angular velocity. Unfortunately, we only had one of these LiDARs, so we got around this, although in theory it's possible, we got around this problem by just incorporating a heading gyro with the Doppler LiDAR to try to recover the full 6-degree freedom velocity and then integrate that for pose. And it turns out that there's some advantages maybe to setting up your estimator this way. These are some equations that are not so important to read, but the point is that the factors that we have to build in this estimator are both linear in the unknowns, which is now just the 6-degree freedom velocity. So we have gyro measurements and we have these radial velocity measurements. So both our measurement models in this problem are now linear. So we can actually just construct this as a fully linear estimator for the 6-stop velocity with this source of measurements. And as a factor graph, you can make that look kind of like this. We still have some motion priors, we have the heading gyros, and then we have some velocity measurements at certain times. And we do all this in a continuous time estimator so that we can account for the timestamps of every one of the measurements. And if you do that, it turns out you can actually do pretty good LiDAR odometry. The quality of it depends a lot on the quality of the heading gyro. We didn't have a great one in this case. Black line is ground truth. Green line is our estimate, which is not as good as the full expensive algorithm that I described a little bit earlier. But we're still sort of on the kilometer scale doing a pretty good job of estimating our motion. And this algorithm runs in just under 6 milliseconds per LiDAR frame. So it's super cheap. You could run this basically on the embedded processor that's right inside the LiDAR without having to tie up your CPU with spending time on this. So we think there's some applications for this. You could probably run this type of odometry open loop for 100 meters, then do a map localization, and that would probably be good enough to produce overall localization results. We then turned our sights to trying to do a similar thing with our radar data. And it turns out the LiDAR guys had done a really nice thing for us, which is that they'd pre-computed all these velocities directly on the sensor. The radar guys didn't do that work for us, so we're working with Navtech. In fact, their sensor doesn't actually normally produce Doppler velocities, but they provided a firmware update for us that was able to kind of at least provide us the raw materials that were needed to then compute the Doppler velocities at every azimuth of our radar. But we actually had to come up with an algorithm that would take the raw returns along every azimuth of the radar, do some correlation. You get very noisy measurements in the radar space compared to the LiDAR signals. So we actually had to run ransack on the estimator that would produce the overall translational velocities of the platform that the radar was attached to. But once we did that, we actually got pretty good quality radar data. You can see this is sort of post-ransack, this video down on the right. Sometimes that's working, sometimes not. Video down on the right is sort of showing the orange is sort of the stuff that's getting rejected by ransack, and then the blue and the red are the velocities that are being accepted by ransack. And if you then put that into an estimator similar to the one we did with the LiDAR, you can estimate the overall motion. And again, we used a heading gyro to recover the angular velocity. In this case, we're doing it only in 2D because this radar is only measuring velocity in 2D. We actually took this out into some fairly challenging scenarios. We went for a nice drive where we went through a progression of more complicated environments, so sort of suburbs where there's lots of usable geometry, highways, then a very, very degenerate tunnel. And then it turned out the thing that was the hardest was actually a very long bridge that went over some water. And so there's almost no geometry off to the sides, not even walls, which made it very challenging to kind of even get the velocity returns. And when we tested our radar odometry now on these different scenarios, you can kind of see, as you might expect, as the environments get more challenging, the baseline algorithms that are doing something like just basic iterative closest point, which are these blue lines, are doing a really poor job of tracking the ground truth, which is the red line in this case. But our algorithm is the green line, which is doing this very low-cost radar odometry. In fact, this algorithm runs in 1 millisecond per radar scan. And so again, could just run basically natively on the processor that's inside the radar. It's pretty much good enough to kind of rely on it for several hundred meters before you get a match back to a map. So we were pretty excited about that because, again, we're using hardware to solve a problem that would have been pretty difficult to do on the software side. Okay, so that's the first part. Now I'm going to talk, that's sort of odometry. The next part, of course, is we want to actually localize. We want to maybe use a map and then predict with our odometry and then correct back to where we think we are on a map with some other measurements. We've been thinking about this problem for quite a while. We've got an ongoing collaboration with General Motors on trying to think about the impact of Canadian weather, I guess the same as Boston weather, on the different components within an autonomy stack for a self-driving car. And my part of that is sort of the impact on localization. And I guess we've been mainly looking at, asking the question, could we take a radar and build a localization and mapping module that works as well as a LiDAR-based module for on-road applications? And we've been focusing on this Navtech radar again. For those that don't know, we actually built a data set called the Boreas data set that's publicly available. It's hosted on AWS. It's a bit unique in a few ways. So it's got this combination of sensors, cameras, LiDARs, and radars. The other thing that's a bit unique about it is we redrive the same 10-kilometer route over and over again over an entire year. Many of the data sets out there don't have this redriving of routes. So we can use any one of the routes for mapping and all the others for localization, and you can swap up those roles. There's a lot of it was over the whole year, so there's several sequences with heavy snowstorms, rainstorms, sunny days, cloudy days, at night in a snowstorm. There's lots of data there that you can play with. And there's even a leaderboard for odometry and localization that you can submit your results to. So I maybe won't bore you too much with sort of the baseline algorithms that we started with, but we took something like iterative closest point, where we're matching point clouds from the live Lidar or radar back to a map that we've generated during a teaching run to build the map. And the baseline algorithms that we built basically perform pretty close to the state of the art for Lidar. So we're getting about 5 centimeters root mean squared error for on-road driving. The radar is sitting at about 10 centimeters, so it's not quite as good as the Lidar yet, but we've got some ideas on improving that, which I'll talk a little bit about those. There's some actual interesting observations you can think about when you're comparing Lidar and radar for localization on the road. For sure, the radar sees through the precipitation better, but surprisingly, the Lidar does pretty well in precipitation as well. There's one situation that we found that was pretty difficult for the Lidar, which was in a snowstorm. And what happened was, as we were driving, ice accumulated on the front side of the Lidar. And it actually just made it impossible for the Lidar to see out through a section of this point cloud. The radar, of course, kept seeing through that, even when it had snow accumulated on it. So Lidar does pretty well in precipitation until you get fully iced up, it turns out. The other thing that's interesting is there's a lot of common structure that you can see between the Lidar and the radar. So you could imagine a scenario where you build a map using Lidar on a nice sunny day, and then you try to localize against it using radar on a poor weather day. So we experimented a little bit with that as well. And you might want to do that because a lot of the existing mapping cars that are out there are sort of more focused on Lidar. So you would still want to leverage that. Again, a bit of an eye chart. This is just saying a little bit what I said before. Our Lidar localization, so build a map and localize with Lidar, is sort of down to about 4 centimeters, actually, in terms of accuracy, root mean squared error. Radar is somewhere around 7 centimeters. And then building a map with Lidar and localizing with radar is a little bit worse. It's at the moment sitting around like 13 centimeters of error, root mean squared. So there's some work to be done. The change in modality is a bit tricky. One's 3D, one's 2D. How do you turn the Lidar map into a 2D map for the radar to localize? There's some open questions there. So one of the things, in an interest to try to close the gap between the Lidar performance and the radar performance, which was only a handful of centimeters, one of the things we've been thinking about is there's a lot more artifacts in the radar data. So if anyone's looked at radar data, you can see all kinds of strange, there's about 7 or 8 different sources of weird artifacts that happen all the time in radar data. You can kind of see some of them in that video if you look closely. One of the things we thought about doing was just trying to build a network that would build a mask that would decide which things we should pay attention to in the point cloud that came out of the radar. So we think of this as a radar distraction mask problem. And to do this, we actually built a differentiable version of iterative closest point. In this case, our map is Lidar, and we're trying to localize against it with radar. And the radar is being masked by this network that's deciding a weight to apply to every pixel in the radar image. And so we actually gave it a bunch of training poses from ground truth, from a post-processed GPS, and then we just back propagate through this whole pipeline to try to learn this distraction mask network. And at first, it kind of did an obvious thing, which was it sort of ignored things that were further away. But we found some good anecdotal evidence that was learning some things that were a bit better than that. There's some examples where there are some cars in the original data, and those are moving. And by the way, we're not giving it the velocity information in this project. We could probably do that, and it would help. But the mask is able to sort of remove the cars from even the points that are closer to the vehicle. I think this picture is the most compelling one. This is the original radar scan, and this is what it kind of looks like after we do the masking. So there's a bunch of echoes that get removed by the masking. There's some sort of noise that's sitting over here in this field. Often you get these very radial artifacts in the radar data that really don't correspond to any of the geometry in the scene. It's doing a pretty good job of removing those to the point where it actually looks like it's doing something reasonable. So that's been a pretty useful thing. We've probably halved our errors on single frame We haven't actually put that into the full pipeline yet where we can see what the overall comparison to the original 7 centimeter error was. So we're kind of still working on that. Another thing I want to advocate for is a lot of times in robotics, we focus on building new algorithms. We're always trying to build better and better algorithms, right? Build a better mousetrap. I think we could spend more time building analysis tools of our algorithms. And so one thing that we've been thinking about is, can we build a tool that will take an existing algorithm and then decide how well it's going to work, try to predict how well it's going to work in a new scenario? So we're calling, in this case, we're trying to attack the iterative closest point algorithm. And the idea is, under some class of faults that you could apply to the raw sensor data that's coming off the sensor, in this case, Lidar, if you sort of pick a class of faults where, it can't corrupt everything, it can corrupt some percentage of the scan, could you actually work out what the worst corruption is and then see what the effect would be on the accuracy of ICP's ability to localize? So maybe you have some spec, you need to know where you are within 20 centimeters on the road all the time. If there's a big truck that's producing an occlusion, or a whole bunch of big trucks just pathologically are passing your car at the same time and they produce a bunch of occlusions or like shorter ranges that don't match well against the map, could you actually trick the algorithm into producing a bigger error? And we've looked at this a couple of different ways. I won't get into the details, but we had one way where we actually sort of analyzed this in a white box fashion. So we looked at the details of the algorithm and then linearized the algorithm about an operating point and then actually solved an SVD problem to come up with the worst possible corruption to our Lidar scan under some constraints that we couldn't corrupt everything. It's able to do things like take these blue points and sort of shift part of them this way and shift part of them this way, and that produced the largest possible error in our iterative closest point algorithm. And then what you can do is you can take a map that you've built and you can actually apply this corruption scheme everywhere in the map and sort of build a heat map that says, where are the places that are most likely to have large errors if I had the worst case corruptions to my input sensor data? In this case, like red is bad, right? So we learned that there are particular places on this route, and this is a different route off-road for a different type of robot, where we could say those are probably places where localization is going to be a little bit brittle, right? If there's something that's going to corrupt the scan, then you're not going to localize very well there. So, it's a baby step in this direction, but I think it would be interesting to do more work in this area where we can try to find ways of analyzing our algorithms in an adversarial manner. And actually, of course, we live in the era of deep learning, so a second way that we thought about doing this was to just try to train a network that would actually take our input Lidar scan and corrupt it in the worst possible way to maximize our ICP error. Of course, again, under some constraints that it can't just move all the points off to infinity. And it's more subtle than you think, right? Because we're actually trying this on not just a plain vanilla version of iterative closest point, but something that's got trimming, so it's got outlier rejection built into it already. So we can't just move all the points off to infinity to maximize error. The algorithm's smart enough that it knows that there are outliers and it can reject some of those. So you have to move the points just enough that they don't get classified as outliers, but also enough that you maximize the error. And so that's what this network is learning to do. So we can train something that does that. And interestingly, we can again build a heat map that looks at where the worst possible errors that you might get. And it turns out that the previous algorithm that was more analytical and this learned algorithm were predicting very similar hotspots in a map that we analyzed, places that we thought localization would probably be less robust. So this is, I think, kind of encouraging. I think there's some extensions we could do. Right now, if you take a car, it's going to give you this really weird crinkled car. Probably there are some things we can do that will make the corruptions more physically plausible. Some inductive biases that we could put into the network that kind of like focus on, inserting a car in some weird configuration that would maximize the error, for example. Okay, that was the second part of the talk. So we did a lot of stuff on road. Let's move now into the off-road. This is going to be a bit more movies. I have this long-term love affair with this problem of long-range route following off-road. So you're looking at a fairly old video now of a technique that we call visual teach and repeat. So we've driven manually through this environment once, and now we're localizing back against that. So this is a robot driving autonomously. It's had one demonstration of this path. It's only got one laptop, one stereo camera. This is pre-neural networks, so there's no neural networks running on this thing. There's no global map. There's no GPS. There's no IMU. There's really nothing. There's no semantics or structure being exploited. So it's really just sort of tracking low-level features in the visual scene to kind of keep itself on a track. So it knows where it is relative to the path. It's using model predictive control to zero the errors out over time. And we're able to get a robot that drives pretty much exactly in its tracks in most environments without assuming anything particular about the environment. So we've been working on that problem for a long time. One of the things that we've been thinking about more recently is, what happens when there's obstacles that get added to the path between the teach and the repeat. So now you're looking at a more recent video of our Lidar version of this teach and repeat. So this is out at Canadian Forces Base Suffield in Alberta. This is actually their robot. So that's another thing I encourage people to do is pass your code into your collaborators' robots and have them try to run it and see how well it works. That's a real test if you can get it to work on someone else's robot. So this is just using Lidar, again, no GPS, and you can see that there's some obstacles, kind of easy obstacles that it's detecting using a fairly rudimentary obstacle detection, and then it's planning a local path using a sample-based motion planner, which then basically just chooses the right homotopy class to go around the obstacle, and then a model predictive controller that actually refines the path that gets executed. So there's some open challenges that sort of remain for this problem. Like, how do we actually detect these objects? It would be nice to not have to know about the classes of the objects. One of the things I've been trying to get the group to move towards is sort of open vocabulary terrain assessment, like detect that there's things that you don't want to hit without knowing what the classes of those objects are in advance. So there's some things we've been thinking about there. In fact, we've gone back to an old idea. Because we're working now with this Lidar teach and repeat pipeline, this is actually the Ouster OS0 Lidar. And I've been kind of waiting for this sensor to come on the market for 14 years because, as I said earlier, we were thinking about these Lidars as sort of more like an image product, right? When you look at the intensity images. And we had this very bespoke Lidar 14 years ago that was able to do this. It only did it at 2 hertz. It was the size of a microwave oven. And now you can buy the Ouster 128 OS0 Lidar that's like the size of a grapefruit, and it produces images that look pretty good, and they are 360 degrees all the way around. And so you can start to do some interesting things with that. So one of the things, of course, vision processing has also come a long way in 14 years. So one of the things we've been thinking about there is, can we run like Meta's segment anything model directly on these Lidar intensity images to kind of segment out the things that are happening in the scene. And because we're doing teach and repeat, we've already been through the environment once, so we can actually simplify the obstacle detection problem into something that we call the change detection problem, right? We want to compare what we're seeing now to what we saw when we did the teaching of the map. And so the idea that we've been exploring, or one idea that we've been exploring, is we'll segment both. So we'll register the live Lidar scan to the map, and then we'll render intensity images at a common pose. We'll then run segment anything on both of those, which will produce a set of masks. In this case, there's like a barrel that's been added to the scene. When we prompt in that area, we get a very small mask, but in the map, there was no barrel. So when you prompt in that area, you get a very big mask. And you can actually do some kind of 3D intersection over union to kind of compare the masks that you get in the teach and the repeat. And that's a very simple way of finding what's changed in the scene at the object level. And the video on the right, which I should probably just go back and forwards to make it play again. The video on the right, purple is sort of the thing that's being detected as a change. In this case, it's just a person that's standing in the scene. These are fairly early videos. That's a person that the mask didn't match between the segmentation and the two things. But it doesn't know anything about the nature of a person or any of the semantics of that. It's just based on this mask that came out of segment anything. So that's one way that we're thinking about trying to get change detection to happen. I'm also excited that the name of my lab, by the way, is the Autonomous Space Robotics Lab. I haven't really done anything on space in a really long time, but I'm kind of very excited to say that I'm getting back into space robotics now. So the company that I used to work for that Luca mentioned, MDA Robotics, it's actually called MDA Space now, the name keeps changing. They are one of the, so Canada actually committed like $1.5 billion to possibly build the lunar utility vehicle for the Artemis program, or at least one of the competitors, I guess, to build this rover. And so they've asked us to actually try to take our LiDAR teach and repeat and make it the main navigation backbone of the lunar utility vehicle bid that they're putting together. And so we're actually working towards a big demo in the coming months. This is actually from like 2010, I think. We were testing on this vehicle at the Canadian Space Agency. That was probably the last time I did space robotics. And now we're going to be testing on the same vehicle about 14 or 15 years later. But the cool thing is that the lunar utility vehicle finally is the right rover for the navigation paradigm that we built, because most of the rovers that have gone so far are doing science, right? They're sort of doing analysis of rocks and soil and things in the immediate vicinity of the robot, and then they move a little bit and do a bit more. This is an engineer's rover. This is the one that's going to move equipment back and forth between a lander and a habitat. And so there's this defined load transport problem that's inherent to the nature of the rover itself. And so that's exactly why I guess they've asked us to kind of take our LiDAR teach and repeat and try to use it for this program. So stay tuned for more on that. The other thing that's happening with teach and repeat is, of course, because we have a radar, we recently tried to build an off-road navigation scheme based on the radar. We just submitted a paper to ICRA where we talk about exactly that. I was a little surprised that this worked. If you look at the radar scans that it's getting in this like fairly off-road, we talked about what is an off-road environment earlier. This is an off-road environment. The radar scans are pretty non-distinctive. There's not a lot of usable geometry in there that I would have said that the localization would work pretty well. But even just using iterative closest point from points extracted from radar, we're actually able to localize to this path and drive autonomously with sort of like 10 centimeters of root mean squared error. That was surprising to me. I wasn't surprised that it would work in the vicinity of buildings and things like that, but in this vegetation-only environment, I was very surprised that this actually worked well. Key to doing it was that we needed a heading gyro to kind of really get the odometry good enough to sort of last between regions where there weren't a lot of usable features for the radar to match. How good is it? There's some numbers we could talk about. Some heat maps that sort of show where the errors are low, green, where the errors are high, red. But generally it's, we didn't actually have any autonomy failures in these experiments. And the biggest errors that we were seeing were sort of on the order of 0.5 meter in the worst cases. And so radar off-road, I think, is a challenge. If we could get it to work, it would be great, because it means it's going to work pretty much in every weather and lighting condition. And you can kind of see the challenge I'm talking about. This is sort of like easy radar data. There's a fence, there's a tennis court, there's some buildings. You can see this very obvious structure in the data. This is sort of in the flat off-road environment that I just showed the video from. And then here's an environment with a very three-dimensional trail through a forest. And you can see that there's actually ground strikes. Suddenly the radar data becomes short because the robot's pitched and the radar's looking into the ground. That's a bit of a problem. So I think there's still work to be done to make this work on really three-dimensional off-road situations. To that end, we're actually gathering a new data set called the FOMO data set. We're in the process of collaborating with the University of Laval, Francois Pomerleau's lab there, where we're doing something like the Boreas data set, but now off-road, so multi-season through a really challenging off-road forest environment with three-dimensional pitching and all of that. So stay tuned for that. Okay, I think I made it through this part in time to do the last part of the talk, which I wanted to include. So I've mostly been talking about and I saw Russ just came in, so this will probably be the part that he's interested in. I've been mostly talking about the front end part of navigation of mobile robots. Let's turn to the back end now. And so I probably don't need to explain what certifiably optimal is to most of the people in this crowd, because I think a lot of the work originated around here. But just for those that don't know, many of the algorithms that we sort of set up as state estimation problems are basically optimizations, right? And we build a bunch of cost terms, factors if you like, and we're trying to find the x, the trajectory that minimizes that cost. And if you crack open any old book on state estimation, most of the algorithms in those books, we'll basically be finding local minima of those cost functions. And that's kind of a problem, right? So our cost functions may look kind of like this black line. If we start with some bad initial guess, we're going to converge to some point that's far from the right answer. And so what we'd really like to do is have algorithms that find this global minimizing point. So could we do that? And of course, the answer is sometimes. I'm a Canadian, so it can never be yes or no. It has to be sometimes. And there's sort of a well-trodden path at this point. One well-trodden path. Russ has got a different one than this one. But one of them is basically to take this original non-convex problem, to kind of do some algebraic manipulation to put it into another non-convex form called a quadratically constrained quadratic program. But now this has like a particular structure. And then there's a very specific path that we can go to something called a semi-definite program using a technique called Shor's relaxation, which is basically if you define big X to be the original little x transpose, you can exactly transport this problem over here, and then you end up with this rank 1 constraint that you relax, and that's the relaxation. And once you drop this rank 1 constraint, the remaining problem is a semi-definite program, which is a convex problem, which can then be solved with something like iterative interior point algorithm, There's also something called the dual problem, which you can get directly from the QCQP, which is also a convex problem. And so what these techniques are basically exploiting is something called Lagrangian duality. And in general, the original problem will kind of sit here, the convex relaxation will sit here, and the dual problem will kind of sit here. And it's always true that you kind of get this ordering, right? The minimizer of the black line is higher than the blue, which is higher than the orange, or they could be equal. That's called weak duality. When we have strong duality, these things all sort of kiss at a point. So the dual comes up, the convex relaxation comes up, and it touches the minimum of the original function at one point. And so there's a few things you can do there, right? If you can solve the blue problem, and find the minimum of that, which is convex, you're guaranteed now that you found the minimum of the black function. Or you could solve the maximum of the orange one, and that would be also at the same place. And so that's basically what these algorithms rely on. If you want kind of an example, let's take a really simple polynomial problem. It's just a quartic. It's got 2 minima, a red one bad, green one good. If we want to turn this into a QCQP, what we basically do is we define a new state, which is like 1, the original variable theta, and then theta squared. And then we can write this cost function exactly as this quadratic formula. But now there's some dependencies that we need to account for in our state vector, right? We need to say that the first entry of it is 1, and we need to say that the third entry is the square of the second entry, which is this constraint here. But these are now also quadratic constraints. So we have a quadratic cost with 2 quadratic constraints. We can then write that do the standard convex relaxation now, where we drop the rank 1 constraint. And then it's like just a couple of lines of code to solve this using an out-of-the-box interior point algorithm. You can solve that, and out pops the solution. And lo and behold, our solution is rank 1. So since it's rank 1, basically we solved the original problem. We can say that we have the minimizer of the original problem. And you can see that that actually corresponds to the correct value of x and the cost. So very, very simple idea. But to get it to work on big problems is a little bit more challenging. And I guess there's been tons and tons of amazing work. We were not the pioneers in this area. We're followers for sure. Rotation synchronization, where you're trying to get a bunch of rotations to kind of sync up with each other. Pose graph optimization with Dave Rosen and Luca, John Leonard, and others. Really, really amazing algorithm, SE-Sync, that uses some pretty sophisticated machinery to do global optimization of pose graphs. Point cloud alignment, again, Luca and Hank, really, this is actually one of the only examples where you can actually align point clouds in the presence of a lot of outliers and guarantee that you're still finding the global minimum of that problem. There's some really sophisticated machinery. It's a very long paper. The appendices, they ran out of letters. They went like A through Z, and then I think they went back to AA and BB. Like there's a lot of information in there. But I've read it all at least 2 or 3 times. It's a really amazing paper. Some other work that actually came out of U of T with John Kelly's lab, where they were looking at certifiably optimal calibration problems. So there's lots and lots of history of this building up in the robotics community. We kind of jumped on the bandwagon, and we've worked on a couple of things. We were talking about this earlier. So like one thing you can do in this area is to add to the catalog of problems that you can say that there's a global solver for. So we've been working on some things like range-only position estimation. Talked to Alan somewhere around here earlier. He's also got range-only SLAM going on. I didn't mention that on the slide, but that kind of makes this paper kind of boring. We did some like range-only pose initialization, and one thing we did that extended the SE-Sync kind of stuff. Oh, actually, this one first was that we incorporated landmarks. So in the original SE-Sync paper, they were doing pose graph optimization, but there were no landmarks. We showed that we could sort of piggyback on top of SE-Sync and include landmarks and still sort of solve this with the same complexity as a typical local solver for SLAM. And then more recently, we've been looking at sort of matrix-weighted SLAM. So the idea is like in your cost function, you now have like a matrix weight, which could represent some anisotropic noise. Like if you had a stereo camera, you have a lot more uncertainty in the depth direction. You might want to align point clouds under that constraint that you have more uncertainty in some directions than others. It turns out that makes the problem quite a bit harder. Inherently, the problem is actually starting from a quartic instead of a quadratic for that problem. So lots and lots of things that you can add to the catalog that we're by no means done. There's many more things that you could add to the catalog. But we also wanted to take a step back. I'll skip that one, actually. This was something, another catalog item. We also wanted to take a step back and just think about, like, it's actually pretty hard to come up with a new global solver for a new problem. So we wanted to think about how do we onboard people and new problems into the catalog a little bit more easily. And my postdoc, Friederike Dumjen, did a really nice piece of work where she was able to, it's a little bit of a long story, but in some of these problems, when you convert from the QCQP to the SDP, the story is not over. It turns out that that problem actually doesn't produce rank 1 solutions all the time. And so what you can do is you can actually add some more extra constraints, we call them redundant constraints, into the SDP problem that don't affect the original problem, but they reduce the feasible space for the SDP problem. But finding those redundant constraints is not the easiest thing to do in all cases. So we actually built a tool based on Friederike's idea that's able to enumerate all of these constraints automatically just from some it's almost a data-driven approach where we just generate data that satisfies the constraints, which can be done pretty trivially. And then we solve actually a QR factorization, like a null space problem, and out pops all the constraint matrices that we could possibly need. And then we can even heuristically order those constraints and add them into the problem one at a time until we see that the problem actually tightens up again and then we get rank 1 solutions. So here we're trying to like step back and from one particular problem and just think about how do we make it easier for people to bring new problems into the fold. Another thing we've been thinking about at a high level is like, okay, now we've got these SDP solvers. A favorite thing that people like to do these days is actually train neural networks by back propagating through state estimators. So there's tons of good libraries that can do that, but they're all centered on local solvers for the estimator. So we actually showed in this paper, which is under review, but it's on archive, that we could actually compute gradients backwards through our SDP solver for certain problems so that we can now actually train a neural network by having labels at this end and back propagating gradients on those labels through our global solver. So we call that SDP layer. You can combine it with any number of PyTorch layers that you want and try to train things. And there's an example here where we were learning some features for alignment of stereo images. We're training the descriptors of those features, and we're actually back propagating that through one of these global solvers, which didn't seem so obvious that that was going to work, but we can basically say that although now we have like a certified solution in this direction, now we have certified gradients in the other direction. And we showed in that paper that if you actually converge to the wrong local minimum, if it was a local solver and you're back propagating, those gradients are going to lead to wildly bad training of the network. So that's one more thing. And then the last thing that I'll just mention about this stuff is that although there's a lot of these problems in the catalog now, the solvers are not typically that fast. And because we're kind of trying to think about these as generic semi-definite programs, we're applying tools from very, very general tools like Mosaic and these kind of nice SDP solvers. They don't really know about the structure of our problems. And so they're not fast. They're not exploiting the sparsity in the problems. So we had a paper at Wafer last week, again by Frederique, where we were looking at least for a class of problems that actually enjoyed a particular structure called chordal sparsity that we could actually make these problems run much faster. So rather than having one big SDP variable in our optimization, we would identify cliques in our problem, and we would assign one smaller SDP variable to each clique. And then you can actually then just pump that again into a generic SDP solver, but with smaller variables, and then it actually takes a lot less time to solve the problem. Chordal problems are a little bit restrictive, though, but most problems in the category of localization, where you're matching against a map and maybe have some motion model constraints, most of those are chordal problems. But as soon as you have something like SLAM with a loop closure, you now don't have a chordal problem anymore. So we're working at the moment to kind of try to improve this or reduce the constraint that we have to have a chordal problem. This is kind of what happens already in solvers like ISAM2, right? Like they're taking non-chordal problems and they're turning it back into something that looks chordal using like a clique tree. And so we're kind of trying to use those same ideas to think about how we could speed up other types of problems that aren't originally chordal. That's all I've got. I made it all the way through all the slides. Thanks for your attention. I did all the talking, these people did all the work, and these people did all the paying for things. So thanks a lot. Oh yeah, one more quick thing is hot off the presses. I'll just plug this since Luca is here, is that Luca's leading the charge on building an awesome handbook on SLAM, and I'm helping a little bit. And we just actually are about to release the first part of this. So if you're sort of looking for one source to get into how SLAM works and all the neat bells and whistles, hopefully this is going to be the resource in a few years.
The fact that the team is helping is a huge understatement. I think he's doing a lot of the heavy lifting behind that, but thanks for mentioning. All right. Thanks, team. Great presentation. We have time for a few questions. Let's see.
Oh, thanks for wonderful talk, team. I'm just wondering regarding, I'm curious about the resilience in the trajectory. So you mean we can determine, oh, this part could be imprecise or not?
Right, yeah. So the idea with that, you're talking about the attacking the ICP algorithm. So yeah, in that heat map where we have a red area, it basically means that when I take the worst case fault and corrupt the point cloud in the worst possible way at that location, I'm going to produce a final error in the localization of ICP that exceeds some threshold, basically.
Oh, then can he exploit that information in the SLAM or postgraph optimization as a covariance information or some uncertainty?
Yeah, interesting. We haven't thought about that. We thought about it more from the planning point of view. So if you had a route that you'd analyzed and you knew that there were hot spots that were bad for localization, you might actually choose to take a different route through the city, right, to avoid those areas. But I hadn't really thought about it as like quantifying loop closure constraints or something like that. Possibly.
Okay, thank you.
From the attack strategy, do you get suggestions about potential defense strategies? Like,
yeah, interesting. Yeah, I mean, I suspect you could, GANs are a thing, right? I suspect you could probably set up some kind of adversarial situation where you're trying to corrupt the scan worse and worse, but you have some learned component in the algorithm that's trying to reject those corruptions, and they're playing off against each other. Possibly. We haven't gone down that road, though.
Okay.
Hi. Thank you for coming. My question's a bit more high level about some of the sensors you guys have been working with. Obviously, like the more high fidelity, high quality ones can be quite expensive sometimes. Like I know those Ouster Lidars are like tens of thousands of dollars, some of them. So my question is...
2 tens.
There we go. So in terms of scalability / implementing these algorithms in real world scenarios, I know like for maybe something like defense or space, like they're willing to put that money in, but in terms of more commercial use or scalable use for like real world scenarios. How do you anticipate this kind of looks going forward in the sense of trying to introduce these, but worrying about how much money you're spending on them and making them affordable for like actual use in the real world?
Yeah, that's an awesome question. So I guess there's a couple of parts to the answer, right? So one part is that most of the sensors we work with are prototypes. So you're not actually looking at the price right now of what those units would cost if they were being produced at volume on like every car on the road, right? The price is going to drop by orders of magnitude when you do that. Case in point is automotive radars, right? So most modern cars now, at least higher end cars, maybe not the very cheapest cars, but a lot of cars have automotive radars hidden behind the bumpers now. And those were once very expensive, but now because they're on hundreds of thousands of cars, you can build that for tens of dollars. And so I think we can probably expect to see the same thing. Like when I started working with these high-end 3D Lidars, and probably others in the room, they were like $200,000. Now they're $20,000. And we're still using them as prototypes, right? And so the costs are going to go down more and more. But it's a good question, right? Like if you were going to buy a car, how much would you be willing to pay to add the sensors that were necessary for autonomy onto the sticker price of your car? For me, that wouldn't be very much. I kind of like driving, so I probably wouldn't pay more than $10,000 surplus to have autonomy added to my car. And that's basically what all these companies are up against, right? If you want to do it, and that's why most people are not targeting personal vehicles for this stuff anymore. They're targeting things like trucking, robotaxis, where you can put a little more money into the cost of the vehicle because you're going to recover it because it's in higher frequency use. Whereas personal vehicles, it's all about the price point. I suspect we're not going to see autonomy on personal vehicles for a long time.
Cool, thank you. And just a quick follow-up. So do you intend to keep working, like, do you anticipate that LiDAR will remain, if you look at Tesla or something where they're like purely using cameras, like, do you anticipate that there's no need to shift towards like trying to focus on lower cost things now, just like you were mentioning, because of hopefully it'll kind of go down in price eventually?
Okay, I have a bit of a specific viewpoint on this. So I really like LiDARs. What I'm kind of hoping will happen is that there's going to be a confluence of sensing technologies. We're kind of already seeing it, right? One of the LiDARs I have looks like a LiDAR, but it also looks like a camera. And another LiDAR that I have looks like a LiDAR, but it also kind of looks like a radar because it's got the Doppler effect. What I'm kind of hoping is that someone's going to build, eventually all these things will converge, and you're going to get like something that's the size of my fist or smaller that is going to produce high resolution intensity images with depth from the ranges and velocity on every point. And it's all going to be solid state with no moving parts because it's going to use optical phased array technology for the actuation and so on. And it'll all just be printed on one chip. And it'll cost like, I don't know, $10 or something. It's actually kind of surprising. Like there's a LiDAR in my iPad, right? And it's a very small LiDAR. I don't know if you've seen these, but they're basically the size of your thumbnail. What do you think that costs? Yeah, it's about like $3. And it produces a 64 point cloud. Super tiny, very light, low power. So I think we just have to wait. There's a Moore's law for sensors that I think is in effect.
Cool, thank you.
We're already out of time, but maybe if there is a quick final question, I'll try to take it.
By the way, I waited for the LiDAR intensity image sensor, and it eventually did show up. So there's an existence proof.
Thank you for the great talk. Is there, as in your experience as a field roboticist, what's like most underappreciated about actually doing field experiments, and what's most challenging?
Oh gosh. Yeah, we were talking a little bit about this earlier, right? The first 10 years of my career, I pretty much did exclusively field robotics, and none of those papers are cited. So it's a little bit of a thankless endeavor in many cases. The hardest part, I guess, is just doing the experiments in a way that they don't come across as anecdotal. Like no one can repeat them. If I were to do it on another day, I want people to believe that I was thorough enough in my experiments that the results and the conclusions that I drew from the experiments were definitive. And so that's hard, I think, right? If you're trying to compare one algorithm to another, have you designed a broad enough set of experiments that you're going to give some kind of comprehensive answer to the A is better than B kind of conclusion? I think that's really challenging. So I'm not saying I have a way of doing that, but yeah, try to be as comprehensive as you can. And I will just say one thing that isn't exactly what you asked, but like there are categories of papers out there for which you can write a paper where you haven't actually tested a new algorithm, you've just really stress tested someone else's algorithm. Like if you go to the IEEE Transactions on Field Robotics, there's a systems paper, or sorry, a field report paper, said it wrong, field report paper, where you can actually the novelty comes from the way in which you tested the algorithm so that you could actually find out whether A was better than B or like what are the limitations of a particular algorithm. And so there's some incentives out there for doing really good field work if you look for them. Data papers are another one, right? So it's not just about always testing a new algorithm. Got to get a new algorithm, got to get a new algorithm. I think we also just have to be really good experimentalists.
Thanks.
At the risk of abusing Tim's patience, I think there is a request for another question. So last one, make it fast.
Thanks for your time. One quick question about what do you think the landscape looks like in terms of where, let's say, machine learning methods are going to erode away some of the handwritten or handcrafted techniques? I think we're on a trend of, in like Andrew Karpathy's words, right? Software 1.0 getting eaten by software 2.0, and there's that picture that he drew, right? Yeah, where are we there, and where can we be confident in that timeline, or where? I'm just curious about your perspective of where we're at in that trajectory.
Yeah, just one more small question, right? Yeah, I guess I was a little bit of a disbeliever. I was talking about this earlier, but I took Jeff Hinton's neural networks class in grad school, and he taught me all about Helmholtz machines and restricted Boltzmann machines, and I was like, that's not going to go anywhere. I'm going to go over here and do robotics. And then now he has a Nobel Prize, but in physics. And yeah, I mean, you got to open your eyes, right? Like, start using ChatGPT or GitHub Copilot to help write code. Like, it's doing some pretty interesting things. Like, it's not trivial. And so, yeah, we have to be aware of this stuff. Does it mean we have to stop working on all of these other things? I don't think so. I just think you have to find clever ways of dovetailing that stuff into what we're already doing. I guess I'm not really pixels to voltages, deep learn everything. I'm not really on that bandwagon yet. Yeah, photons to atoms, I don't know. I'm not really on that bandwagon yet. I still kind of believe in a modular architecture where I sprinkle machine learning into the appropriate places, but I'm happy to have that debate. Maybe I'll get to retire before I have to acquiesce on that one.
All right, let's thank Tim for an amazing talk.
Thanks very much.